Welcome back. So now we're going to be analyzing the gain when we pick the system response to be the voltage drop across the resistor, VR. So one thing that we're interested when we have an RLC circuit, for example, is to measure how the amplitude of the output compares to the magnitude of the input. In order to do that, we have to look at the magnitude of this complex number. So that's what we call the gain, little g. It's much easier algebraically to work with the magnitude squared. So for now, we're going to work with little g squared, which is defined as the magnitude of big G squared. Okay, what is that? We can calculate it by looking at the magnitude of the numerator divided by the magnitude of the denominator. So the magnitude squared of the numerator is given by r squared omega squared, and then to calculate the magnitude of the denominator, we take the real part squared plus the imaginary part squared. So that is given by 1 over c minus L omega squared, everything squared, plus r squared omega squared. And now we have an expression for the square of the gain given here. Some questions that we're interested in asking is, what happens as we vary omega? So let's look at some extreme cases. So what happens when omega goes to 0? That is, if we're driving the system with small frequencies. So let's look at this expression. If we plug in omega equal to 0, the numerator is equal to 0 because we have an omega squared here. But the denominator is not, because there's a term here that is a constant. So when we divide 0 by a constant, we recover that g squared goes to 0. So the gain goes to 0 as omega goes to 0. What happens at the other extreme when omega goes to infinity? So again, we look at this expression and compare the behavior of the numerator and the denominator. So the numerator is growing as omega squared. That's their largest term. Whereas the denominator is growing as omega squared squared, which is omega to the 4th. So the denominator is growing faster than the numerator. Therefore, g squared tends to 0 as well. So if we drive with small or large frequencies, the gain goes to 0 in both cases. All right, so we could use the gain in order to obtain this information, but sometimes that can be messy. The expression might not be as clear as this. In those cases, it's helpful to think about the complex number big G of R and analyze that separately. So let's do that now. So here I have that big G of R as omega goes to 0. So the complex number on top in the numerator becomes 0 because we have IR omega and omega goes to 0. And the complex number in the denominator goes to 1 over c. So again, we recovered the same result, that the complex number tends to 0, and therefore its magnitude tends to 0. Now what happens at the other extreme? So as omega goes to infinity, we have that the numerator is growing as IR omega. So that's the dominant and the only term in the numerator, whereas the denominator has a dominant term that looks like minus L omega squared. And again, if we look at the behavior, omega going to infinity, this number is going to 0 because the denominator is growing faster than the numerator. All right, so here we have the extreme behavior of the graph, of the behavior of G. Now, what happens in the mid-range? What happens for values in between 0 and infinity? So let's look at mid-range values of omega. One behavior that we're interested in is, what is the maximal gain that we can obtain? So one thing that we can do that we learned from calculus is that if we take the expression for the gain, g squared, and take its derivative, set it equal to 0, this would give us the value of omega that gives us maximal gain, or maximal gain squared in this case. But if we try to take the derivative of this expression, you soon find that this is pretty messy. So this will be a challenge that we don't necessarily have to do. This is a case where dealing with the complex numbers and thinking about big G of r will be very helpful. So let's look at the magnitude of G of r, which is given by the magnitude of its numerator divided by the magnitude of its denominator. Now we're comparing the magnitude of two complex numbers. So let's draw that in the complex plane. So here is the real axis, and here is the imaginary axis. So the numerator is a purely imaginary number, I r omega. So we plot that on the imaginary axis. And this is the value I r omega. And then the denominator has the same exact imaginary part. So it will also have this imaginary part, but it also contains a real part given by 1 over c minus L omega squared. So the complex number looks like this in the complex plane. So we have a numerator that's purely on the imaginary axis, and we have the denominator, which is drawn here in orange, that has a real and imaginary component. So we're interested in the length of these two complex numbers. So just by looking at the graph, we can see that the length of the denominator is greater than the length of the numerator, unless we have a very specific case where the real part of the denominator goes to 0. In that case, the two vectors would be, the two complex numbers would have the exact same magnitude. So when does that happen? We want the real part of the denominator, which is given by 1 over c minus L omega squared, to be equal to 0. Solving this, we obtain that omega is equal to 1 over the square root of LC. So note we're thinking about frequency as a positive number. That's why we don't have a plus or minus. So this is the frequency where the gain is maximized. So instead of taking derivatives of a complicated expression, we were able to do this simply by thinking about the geometry of complex numbers. And now we have the value of omega that gives us the maximal gain. Now, what is that gain? So what happens when I plug in omega equals to 1 over the square root of LC into this expression? Again, the real part of the denominator goes to 0. So I'm comparing the magnitude of I r omega with the magnitude of the same thing, I r omega. So this tends to 1 as omega tends to the square root of 1 over LC. So we have found not only the frequency where the maximum happens, but that the maximal value that the gain takes is 1. That is, the amplitude of the output is at most the same as the amplitude of the input. That's why we have a 1 over here. And now we have all the ingredients to plot what the gain looks like as a function of omega. So we found as omega goes to 0, the gain goes to 0. As omega goes to infinity, the gain also goes to 0. And then for this specific value of omega, omega equals 1 over the square root of LC, the gain goes to 1. So let's make a plot with all this information. So here on the x-axis we have omega, our input frequency, and on the y-axis we have g, little g, the magnitude of the complex gain. Again, as omega goes to 0, the gain goes to 0. As omega goes to infinity, the gain also tends to 0. And then we found that for omega equals 1 over the square root of LC, g obtains a maximum, and that maximum is equal to 1. So we know that this point is on the graph. And therefore, the graph of little g looks something like this. All right, now let's do some exercises in practice.